In this assignment, we will compute elevation raster maps from scattered point data using different interpolation techniques. After starting GRASS, I will create a new map set for topic 4. Assignment 4. And as with the previous assignments, I will change to the working directory where we will store the images for our papers. So I will create a new subdirectory, homework 4. Okay, so I think we are set to begin. So for the first part, we will create the elevation raster from the randomly distributed points using nearest neighbor interpolation based on Voronoi polygons. So let's first set our spatial region and resolution. And we will use a predefined region, a small rural area near North Carolina State University, and we will set the resolution to 1 meter. Then you can run the erase if you still have some layers in your map display. I don't need to run it, but let's now run the computation. So as the first step, we will take the random points and then we will convert them to Voronoi polygons. And as you can see, I have this little orange rectangle here. What do I need to do to see the result? I need to zoom to computational region because my display is still set to the region from our previous assignment. So let's just zoom to computational region. And now I have Voronoi polygons around every point in my data set. So let's now display these Voronoi polygons, as colored areas and as centroid, and these centroids actually show the location of the input points. So you can see lots and lots of polygons, and each of those polygons has a single point, and that single point is the actual input point. And you can zoom in if you want to explore how they look like. Now what we would like to do, this is all vector data and vector polygons. So now we want to convert them to raster representation. So let's look at what kind of categories and what kind of attributes do we have in this polygon data set. So we have two columns. One is integer and represents the category. That's essentially a number of the polygon. And the other one is double precision and has a value. And this is where we have the elevation stored. So we can use it to assign the value to the raster based on these polygons. So we will convert the vector polygons to raster that will represent the Voronoi polygons as raster file with elevation assigned to each of these polygons. Okay, so as you can see, now we have that elevation pattern. We can change the color to elevation color ramp that we have used in our previous assignments. And you can see the Voronoi polygon pattern already in the elevation data. And just to highlight how the structure of this digital elevation model looks like, let's compute aspect map. And you may recall that we have used aspect map to look for artifacts in the when we did the resampling assignment. So here again, we will be using the aspect to better see the structure of the digital elevation model. So as you can see, the aspect really includes a lot of black areas. When you query those black areas, so let's just do them. So this is aspect. We can query them. And you can see it says no aspect. So now you think about in what areas we don't have any aspect. And when you go back, when we were talking about nearest neighbor resampling, then you can see that these are actually flat areas that have assigned the same elevation value. And we can just confirm that by looking at our digital elevation model in 3D. So let's just switch off the aspect and the vector data, and let's just have only the raster elevation map on, and we can switch to 3D view. And let me just grab this out. And let's change the resolution to full resolution so that we can actually see the structure of the digital elevation model. Maybe we can exaggerate the elevation a little bit. So now you can clearly see that we have this that the entire digital elevation model consists of these flat patches. And that are typical for nearest neighbor interpolation. So let's go back to two-dimensional view. And for your report, please save the aspect map. And we can also add the given points just to highlight how these points are located within those flat polygons. So now you can see them. And we can also add the legend for the aspect. Let's just make the legend a little bit smaller. So you can see that the most of the values are black, and that's the aspect that's actually not defined. And then only these edges of the Voronoi polygons have some defined aspect that ranges from 0 to 360. So now let's explore the inverse distance weighting method. So again, we will be working in the same region. So you can rerun that command, or you can just skip it. Again, we will be looking at the at what kind of variables we have there or attributes that we can use. So again, we already looked at that, and the elevation is stored as double precision attribute named value. So we can now interpolate the elevation map using the default parameters of the IDW method using the command vserf IDW. So again, we got the resulting digital elevation model. We can change the color just to be consistent with all the other elevation maps that we are using. And now let's look at the aspect map. Again, now this looks better. We don't see any of those flat patches. But as you can see, this digital elevation model also includes some artifacts. Again, the aspect will be, the legend will be the same, but these little dots, little peaks, and little pits are located in the given points, and you can verify that by displaying those points. And we can try to improve this output by choosing different interpolation parameters for the IDW method. So I would like to ask you to actually open the manual page for the command vserf IDW. So you can either Google it or you can open it here in the within the, when you look at the tools. Look at all different parameters that you can select there, and that would be the power parameter and the number of neighboring points, and then compare the outputs for different power parameters. The default is P equal 2, and number of neighboring points. Again, what we have here was generated with 12 neighboring points. So please increase it, decrease it, and comment on what kind of results you have. And you have to think about how to design this experiment so that you can actually draw some valid conclusions. And again, you can either use aspect the same way as I used it here to compare the outputs, but you can also use the three-dimensional view as I used for the Voronoi polygons-based digital elevation model. And it is also useful to look at the histogram and look at the R.Univar, the summary statistics. So now let's move on and look at another interpolation method that is available and that is sometimes useful when the input data are not scattered points, but when the input data are contours. So again, we will be working with in the same area. Let's just erase the layer manager so that we don't accumulate too many points, too many maps there. And let's now run the interpolation from contours. So we will work in the same region. We will take the contours that are available in the permanent map set, and we will convert them to raster representation using this command V to rast. And you can display for yourself these contours just to see how they look like. I think we have them displayed later on. So here is the raster representation of those vector contours that are available in the permanent dataset. And now we will use the contour-based linear interpolation to essentially create a raster from this continuous raster, because here you can see like these white areas, there are no values there. So now we want to fill in those white values. So again, we will change the color table. And and we will check the structure of the digital elevation model using the aspect, looking for any possible artifacts. Okay, so it looks pretty good. We have some artifacts in this area where the contours were farther apart. And let's just add those original vector-based contours here. We can make them slightly transparent so that we can see the output better. And you can save this output for your report. So let's just do that. And the final method that we will work with will be the triangular irregular network model, which will be a vector representation of the digital elevation model. And this is really optional, so I'm just adding it as it is another commonly used method when you want to do a vector representation of DEM. So we had converted the points that we had where the attribute, where the elevation was stored as attribute, but now we will convert that attribute elevation value to actual Z value for that vector points. And then we can generate the Delaunay triangles. And then we can color these triangles based on the associated elevation. And we get the vector representation of that elevation data. So these are polygons, and those polygons are colored based on the elevation. So now this is all that is for this assignment. The most work is really for you to generate that experiment for inverse distance weighting method. And for those of you who are familiar with Python, you can use this script to actually compute that experiment automatically, including the outputs and including the report.